Welcome, dear students. I am Dr. Arun Kumar, Associate Professor, Department of Mathematics, Sai Vidya Institute of Technology. In my last video, I discussed about the method of finding the rank of a matrix, which is the first and a basic and a very important concept in linear algebra. In this video, let us learn how to solve a system of linear simultaneous equations using one of the easiest method, that is Gauss elimination method. So to begin with, let us discuss the working procedure, that is the method of solving a problem. So I'll say how to solve a problem stepwise. Then we'll use that procedure to solve a few examples and we will see what is the solution. So step 1, given a system of equations, we write the augmented matrix A colon B, where A is the matrix of coefficients and B is the matrix of constants. So when the system of equations are given, so let us write what is the coefficient matrix and constant matrix. We'll join them. So that resultant matrix is called as augmented matrix. So I'll explain this later with an example. Second step, after writing the augmented matrix for a system, we apply elementary row operations and we reduce the given augmented matrix to row reduced echelon form. The echelon form means it is nothing but a matrix of the form in which the principal diagonal elements below the principal diagonal are zeros. First step, once we get an echelon form, we write the system of equations for that echelon form matrix and solve them by using back substitution method. We get the values of x, y, z, the solution of a given system of equations. So these are the three steps involved in solving a linear simultaneous equations using Gauss elimination method. A very easy procedure here. So here first let us discuss how to write an augmented matrix. Augmented matrix. See, if I have a matrix A like this, a 3 cross 3 matrix, and a matrix B, column matrix, which is a matrix of constants, then the augmented matrix A is to B, A colon B, can be written like this: a coefficient matrix A colon the constant matrix 1, 2, 3. So just you have to join them using this symbol. Now let us see how to solve the system of equations by using this Gauss elimination method. The procedure, whatever we have discussed in the previous slide here, let us see how to apply this to solve a problem. So I'll take a first problem. Solve the following system of equations by Gauss elimination method. So these are the three equations we get. So if you want, you can solve these three equations using your calculators. So three equations in three unknowns we have. You can make use of our calculator to solve. If you solve by using your calculator, you come to know what is the solution. Let us see how to apply Gauss elimination method, and we'll check the solution with the answer whatever we get in the calculator. The first step of your working rule says we have to write an augmented matrix for a given system. So the augmented matrix for a given system of equations is A colon B equals the coefficient matrix A. See, it is a matrix of coefficients. See, the coefficients means the first equation, the coefficient of the variables x, y, z are 1, 1, 1, and the right hand side, the constant was 9. So I can write the first row like this: 1, 1, 1, colon 9. Second equation represents the second row. The coefficients are 1, -2, 3, and constant was 8. So it is 1, -2, 3, colon 8. The third equation is third row elements here. So the values are 2, 1, -1, colon 3. So 2, 1, -1, colon. So this is how we can write the augmented matrix A colon B for a given system of simultaneous equations. So this is the first step in solving a problem. So once you write the augmented matrix, we know the second step says we have to reduce this augmented matrix to echelon form. So this echelon form we have already discussed in the problems of rank. So let us apply the same procedure. So we know echelon form means the leading entry of each row must be a non-zero element. The elements below the leading entry must be zeros. A number of zeros in each row must be greater than its previous row. In other words, in one line, we can say an echelon form like this. It is a matrix in which the elements below the principal diagonal, I mean this is the principal diagonal here, elements below this principal diagonal are these three elements, 1, 2, 1. So these three elements should be 0. So if you make these three elements 0, so the resultant matrix is said to be in echelon. And you know this can be achieved by using row operations. So let us start the procedure of reducing this matrix to echelon form. And remember, in this you have to use only the row operations. Don't use column operations. First, in the first step of echelon form, you know, we'll concentrate on the first row. So check the leading entry of first row. So leading entry of first row means it is first row first element, that is this 1, and it should not be 0. If leading entry is non-zero, we can write that row as it is, and we have to make elements below the leading entry 0. That means this is the leading entry, means the element below this leading entry are this element 1 and 2. So we have to make these two elements 0 using row operation. I mean you have to operate R2 and R3 with R1 only. So what are the operations? See, now we apply elementary row operations and reduce the above matrix to echelon form as follows. I will use this operation. R2 implies, you can take minus R1 plus R2, or I can say R2 minus R1. If I subtract these two, you know 1 minus 1, it becomes 0. So this element becomes 0. I can replace that in second row first element. So let us apply the same operation for all other elements. So this is the operation I can use to make this element 0, because these two are same, just subtraction. And similarly for third row, we have 2 here. You have to make this element 0 using R1 element only. So the R1 element here is 1. So what I'm going to do is, let us multiply this by minus 2. So if you multiply by minus 2, and add with this minus 2 plus 2, it becomes 0. So I'm taking the operation. R3 is minus 2R1 plus third row R3. So if we use these transformations, the first step matrix becomes A colon B is equivalent to, say I'm writing first row as it is, 1, 1, 1, colon 9. So this element, if you use the operation, see, R2 minus R1, 1 minus 1, 0, minus 2 minus 1, minus 3, 3 minus 1, 2, 8 minus 9, minus 1. And this is minus 2 times R1, means you can multiply this by minus 2. So I get minus 2, minus 2, minus 2, minus 2 into 9, minus 18. Add with the last row. Minus 2 plus 2, 0. Minus 2 plus 1, minus 2. Minus 2 minus 1, minus 3. This is minus 18 plus 3 minus 15. So if I use these operations, we get this. Now the next step is, we'll go to second step, next stage in echelon form. So in the next stage, in the second stage, we will concentrate on the second row, and the leading entry of second row is the second element, that is this minus 3, and which is non-zero here. So once this is non-zero, so this will be taken as leading entry, and element below the leading entry, that means this minus 1, should be 0. So in the next stage, by writing first row and second row as it is, let us apply row operation, and we will make this element 0 using second row element R2 only. So the operation is R3. So I'm changing third row, this element. So R3 implies, see here we have 3, here we have 1. So let us multiply this by 3. So if you multiply this by 3, you get 3, and here also 3. Minus 3 minus 3, subtract. So R2 minus 3 times R3. R2 is minus 3. So minus 1 into this minus 3 becomes plus 3. So plus 3 and this minus 3 gets cancelled, we get 0. So if I use this transformation, this element becomes 0. Minus 3 minus of this minus plus 3. So we get A colon B is, see, the first two rows we have written as it is, and for third row we are applying this. If you apply, the element below this, it becomes 0. This is 0. And apply the same operation for the next two elements. So the next two means R2 minus 3 times R3. R2 is 2 minus 3 into minus 3 plus 9. So it is 2 plus 9, it becomes 11. And this is minus 1 minus 15 into minus 3. So minus 15 into minus 3 is minus 40 plus 45. 45 minus 1 is 44. Right? So if you apply this transformation, this is the matrix we get. And if you observe this matrix, this is the principal diagonal. And we can observe that all elements below the principal diagonal are 0. These three elements what we have here become 0. So once we get a matrix like this, that is called as an echelon form matrix. So the augmented matrix, what we have written here, reduces to echelon form, and this completes your second step of working group. The first step is writing augmented matrix. Second step is a reduction of this augmented matrix to echelon form, and that we have achieved. And the last step of Gauss elimination method says, for this echelon form matrix, we write the equations and we solve them. If we solve the equations, we get the values of x, y, z, which is the required solution. So how to write the equations for this? See that the matrix 1 is in echelon form, hence the system of equations for matrix 1 is given. See, we will write from last row. So instead of writing from the first row, I'll start from last row, so it is easy to compute. Remember, this column is with respect to x, this is y, this is z, and this is constant. So for the last row, x is 0, y is 0, but z is 11. So I can write like this, 11z is equal to 44. So equation will be written like this, 11 into z is equal to 44. So if 11z is 44, then z is 44 by 11, it gives 4. So one value, z value, we got. Now, once the last row is over, we'll go to its previous, second row. See, from second row, what is the equation? X is 0, y is minus 3. So I can write minus 3y Z is 2, so it is plus 2Z. So minus 3y plus 2z is equal to minus 1. Minus 3y plus 2z equals minus 1. And I need y here. So take this term to the other side. So it is plus 3y is equal to, take minus 1 to the left hand side, it becomes 2z plus 1 plus an interchange. I will take minus 1 to the LHS, minus 3y to the RHS. So I get 3y equals 2z plus 1, and this is equal to 2 into, z is 4, let us substitute here, 2 into 4 plus 1. So this is 8 plus 1, that is 9. So I get 3y equals 9, then y is 9 by 3, we get 3. So this is the value of the second variable. Now, the last one from first row. So I'm going from last to first. The first row, what is the equation? X is 1, y is 1, z is 1. So I can write x plus y plus z is equal to 9. See this. X plus y plus z is 9. So I want x here. So x is equal to, it is 9. Take these two terms to the RHS. We get minus y minus z. And this is equal to 9 minus y. Y is 3 and z was 4. So we get 9 minus 3 minus 4. So we get x is equal to 2. So we get the value of x, y and z. So the complete solution of a problem is x comma y comma z equals 2 comma 3 comma 4. So this is the solution of your given system of equations according to Gauss elimination method. So this is how we can solve a linear system of simultaneous equations using the easiest method is called as Gauss elimination. So this is a common procedure we can apply for any problem. So if you solve these equations using your calculator also, you get the same answer, 2, 3, 4. You can cross check. So solve 3 equations in 3 unknowns using calculators. We get 2, 3, 4 as a solution. So let us continue. I'll take one more problem, the second one. Solve the following system of equations by Gauss elimination method. So these are the 3 equations given. So as usual, the first step is the augmented matrix for a given system of equations. So A colon B. So the first equation gives the first row. So what are the coefficients here? 2, here it is 1, here 4 is equal to 12. So I can write 2, 1, 4, colon 12. The second equation gives the second row. The coefficients are 4, 11, minus 1, 33. So I can write 4, 11, minus 1, colon 33. The third, the coefficients are 8, minus 3, 2, 20. So I can write 8, minus 3, 2, colon 20. So this is the augmented matrix for a given system of equations. So this completes your first step of Gauss elimination method. Now the second step. The second step says reduce this augmented matrix to row reduced echelon form. So now we apply elementary row operations and we reduce the above matrix to echelon form. So what is echelon form? This is the principal diagonal. We have to make the elements below this principal diagonal, that is 4, 8 and minus 3, to 0 using row operations. So as a part of that, in the first step, you will concentrate on first row. So according to the procedure, the first row, first element, that is 2 here, it is a leading entry and it should not be 0. And we have 2 in it. So according to the procedure, if this is the leading entry, elements below the leading entry must be 0. That means this 4 and 8 should be 0. And you have to make them 0 using the first row, R1. So what are the operations I can use? R2. So to make this element 0, I'll multiply this by minus 2. See, minus 2 into 2, minus 4. Minus 4 plus 4 becomes 0. So I can use this operation. Minus 2r1 plus r2. And to make this element 0, I can multiply this by minus 4. I should operate with r1 only. So it is minus 4 into 2, minus 8. Minus 8 plus r3 is 8. Minus 8 plus 8, 0. So I can use this. Minus 4r1 plus r3. So these are the two transformations I'm going to apply for these two rows to make these two elements 0. So if we apply, we get A colon B equals 214 colon 12. So this, minus 2r1 plus r2, minus 2 into 2, minus 4, minus 4 plus 4, 0. Next element, see, minus 2 into 1. So it is minus 2 plus r2. R2 is 11. So minus 2 plus 11. So it is 9. And coming to the next term, see, minus 2 into 4, minus 8, minus 8, minus 1, minus 9. The last term, minus 2 into 12, minus 24, plus 33. So minus 24 plus 33, again it is 9. Now the third row, so it is minus 4r1 plus r3. See, minus 4 into 2, minus 8. Minus 8 plus 8, the first term was 0. Whereas second term, see, 1 into minus 4, it is minus 4. And we have minus 3 here. Minus 4, minus 3, minus 7. And this is 4 into minus 4, minus 16, plus 12, plus 2. So minus 16 plus 2, it is minus 14. And next, this is minus 4 into 12 plus 20 gives minus 28. So this is the matrix of the first stage. Now in the next step of echelon form, in the second stage, we are going to concentrate on second row. So according to the procedure, the leading entry of second row, second row, second element should not be 0. And here we have 9. So this is the leading entry now. So according to procedure, the element below the leading entry must be 0. So that means we have to make this minus 7 0 using this second row element. For this, the operation we can use is R3 implies, let us cross multiply 7 into this, 9 into this. 7 into 9, 63. Again here 9 into 7 is also 63. 63 minus 63 becomes 0. Right? So I will use this operation. 7R2 plus 9R3. So the matrix becomes, I'm writing first two rows as it is. 2, 1, 4, colon 12, 0, 9, minus 9, colon 9. With this term anyway it becomes 0. So apply this transformation for the last two elements. The minus 9 into 7, minus 63, minus 14 into 9, minus 126. So minus 126 minus 63, it gives minus 189. And similarly, this is 7 into 9, it is 63, minus 28 into 9. So it is minus 28 into 9 plus 63, gives again minus 118. So this is the matrix we get. And if we observe this, these are the elements in the principal diagonal. Now, let us rewrite the equations for this echelon form matrix. So thus the matrix 1 is in echelon form, hence the system of equations for this matrix is. So as usual, like a class problem, so we'll start from the last row. So the last row is, so x is 0, y is 0, the value of z is minus 189. So I can write minus 189 into z is equal to the right hand side minus 189. So z becomes minus 189 by minus 189, which gives 1. So this is the solution for z. Now using second row, we write the next equation. from second row. Here, the coefficient of x is 0, y coefficient is 9, and z coefficient is minus 9. So I can write 9y minus 9z is equal to RHS is 9. So 9y minus 9z equals 9. So I want the value of y. So I'll keep this 9y here and take this term to the RHS. So I get 9y is equal to, so it is plus 9z plus 9. So this is equal to 9 into, z is 1. So it is 9 into 1 plus 9. So it is 9 plus 9, 18. So I get 9y equals 18. So this implies y is equal to 18 by 9, 2. So similarly, from the first row, we get the equation C. This is 2x plus this is y plus 4z is equal to 12. So I want x here. So I get 2x equals, it is 12. Take these two terms to the right hand side. It is minus y minus 4z. So on simplification, we get 2x is equal to 6, or x is 6 by 2, 3. So I got the values of x, y, z. So the complete solution of the given system of linear equations is, it is x comma y comma z equals 3, 2, 1. So this is the required solution here, and this is how we can solve a given system of linear simultaneous equations using Gauss elimination method. And if you use your calculator and solve these three equations in three unknowns, we get the same solution, 3, 2. You can check your solution using calculators also. So this is a common procedure to solve a system of linear equations using Gauss elimination. So in the same way, so I did one more problem here. Solve the following system of equations by using Gauss elimination. Again, three equations in three unknowns we have. So let us apply Gauss elimination method and solve this. So as usual, according to the working rule, the first step says we write the augmented matrix for a given system. So the augmented matrix is A colon B equals, see the first row will be written using first equation 5, 10, 1 colon 28. From second equation we can write second row. This is 1, 1, 1 colon 6. From third equation we can write the third row of augmented matrix. It is 4, 8, 3 colon 29. So this is how we can write the augmented matrix for a given system. Now this is the first step. The second step of Gauss elimination method says apply row transformations and reduce this augmented matrix to echelon form. So this is the principal diagonal here, 5, 1, 3. So make the elements below this principal diagonal, that is 1, 4, 8, 0, using row operations. Now as usual, in the first stretch, I'll make these two elements 1 and 4 0 by operating these two rows R2 and R3 with the first row R1. Now we know here we have 1 and here we have 5. To make this 0, I can use the transformation like this. R2 implies it is R1 minus 5 into 1, that is 5 times R2. So 5 into 1, 5, 5 minus 5 becomes 0. And similarly, to make this element 0, 4, I'll cross multiply. I'll multiply this by 4, this 5, 5. So 4 into 5, 20. And here also 5 into 4, 20. So 20 minus 20 becomes 0. So I can use this transformation. R3 equals 4 times R1 minus 5 times R3. So these are the two operations I can use to make these two elements of the first column 0. So let us apply. We get, see, first row we have written as it is 5, 10, 1, 28. If we use this, see, R1 is 5 minus 1 into 5, 5, 5 minus 5, 0. Second, R1 is 10, minus 1 into 5, 5. So 10 minus 5, 5. This is 1 minus 5, we get minus 4. And this is 28 minus 5 into 6, 30. So 28 minus 30, minus 2. And for the third row, if you use this transformation, so 5 4s are 4 5s are 20, 20, so it becomes 0. And coming to the next element, see this. 4 into 10, it is 40, minus this term, 8 into 5, again 40. 40 minus 40 is also 0. This term was 0. And here the next element, 4 into 1, 4, minus 5 into 3, 15. It is 4 minus 15, you get minus 11. And the last element, 4 into 28, minus 29 into 5 gives minus 33. So if I use these two transformations, your augmented matrix reduces to this. And here, in the first step itself, the augmented matrix, when you apply this row transformation, directly it reduces to echelon form. Because if you see this is the principal diagonal, 5, 5 minus 11, and elements below the principal diagonal are already 0. So no need to continue, no need to go to the next step. It is already in echelon. So, once it is in echelon form, we'll write a system of equations for this matrix and solve. We get what is the value of x, y, and z, which represents the solution of given system. So let us write the equations starting from last row. We'll write from last row. So here, see, x is 0, y is 0, but z coefficient is minus 11. So it is minus 11 into z is equal to RHS minus 33. See this, minus 11z equals minus 33. So z becomes minus 33 by minus 11. It gives 3. Now, using second row, we'll write the second equation. So second equation becomes x is 0, y coefficient is 5, so it is 5y, minus 4z is equal to minus 2. 5y minus 4z equals minus 2. So I want y here. So 5y equals, take this to the RHS, it becomes plus 4z minus 2. If I take this to the RHS, it becomes plus 4z. Now 4 into, z is 3. So get 4 into 3 minus 2. This is 12 minus 2, 10. So get 5y equals 10. Then y is 10 by 5, 2. So this is the value of second variable. Now at the end, using first row, we write the last equation. So from the first row, x coefficient is 5. So it is 5x plus 10y plus z is equal to 28. 5x plus 10y plus z equals 28. So 5x equals, I want x. 5x equals, it is 28. Take these two to the right hand side. It is minus 10y minus z. So y is 2 here, 10 into 2, 20. So it is 28 minus 20 minus z is 3. So on simplification, we get 5. So that 5x equals 5. Then x becomes 5 by 5, 1. So we got x is 1, y is 2, and z is 3. So the complete solution of a problem is x, y, z equals 1, 2, and 3. So this is the required solution of your problem. So this is a common procedure for any problem in Gauss elimination. So this is how we can solve. So by practicing these 3 problems, you can solve 3 more problems given here. 1, 2, and 3. These 3 problems, you try using the Gauss elimination procedure. All the best. Thank you very much.